Well, welcome back to the Math Zone. We're going to be doing this this worksheet. Oh, and the worksheet itself. Let me see if I can find it. Give me a sec here. Here it is. Yeah, I like it better on my PowerPoint if it'll work. Yeah, there we go. So this is the PowerPoint that I'd planned to use, but you know, best laid plans. Let's see, add to existing node. We're going to add it to this. Okay, should have done that before. So I only wanted to do that because I have the diagram for this, I believe. Didn't I put it in here? Yeah. Anyway, this is sort of a cleanup of some of the things that, with all these days off that we've had, the things have just fallen through the cracks. And so I was going to try to pick up the pieces. So we're going to pick up the pieces now. So first things are projections. So projections are just a way of computing the portion of a vector that points in the same direction as another vector. So, can I get this to go up there? Sure. So one way to look at it is that that this projection down here, if you look at the projection of B onto A, it's kind of like if you had this very bright light, or if maybe you're out in the sun. There we go. That's not a very good sun. But anyway, you're out in the sun, and the sun is shining, and it makes this vector B cast a shadow onto vector A. And so the shadow, that's the projection. So anyway, it's kind of like what you would get if you flattened vector B down onto vector A. It's pretty easy to figure out the formula for this. And one other thing is that this projection, if vector B is kind of pointing away from vector A, then it's okay. You're just, because shadow's going to end up falling on the ground behind vector A, if you will. So this is what the picture looks like if you have an obtuse angle between the two vectors. Anyway, you can pretty easily figure out this vector projection. I'll start by computing the length of this. So here's this angle between these two, and you know that the cosine of the angle is going to be A dotted with B over the magnitude of A times the magnitude of B. So that's the cosine of that angle. And then, since this is a nice right triangle here, the length of this is going to be related to the cosine. In fact, the cosine is, so the cosine of the angle will equal the magnitude of the projection. We'll just do it that way, over the magnitude of B. Okay, well, let's combine these two, and you have that A dotted with B over magnitude of A times magnitude of B is equal to the magnitude of the projection over magnitude of B. And let's just cancel those. And so this projection, the magnitude of it at least, is just the dot product over the magnitude of A. Now, if you want the actual vector, the actual projection, that's easy enough. Take this and multiply it by A dot B, magnitude of A, multiply it by A over the magnitude of A. And typically, this is usually going to be written like this: A dotted with B over the magnitude of A squared times A, or something like that. The main thing that's confusing about this for most people is that you're projecting B onto A, and there's a lot of A's here. There's only one B. So this particular formula. Here we go. So this is the length of the projection, and this is the actual projection itself, the actual vector. So here's the sort of problem, or at least a couple of problems that we're going to be doing. I want to find the vector, so let's see, CD. So I've given you some information here. I've got this nice diagram. This is on your worksheet. And so let's see if we can figure out, wait, which one are we doing here? Oh, vector CD. Okay, so we're going to call this, let's do it this way. We'll call this vector A, and that's the vector, let's see, we're going back 4 and down 3. And then this one here, that we're going to call vector B. Whoops. And that's the vector -3 and up 1. And now what I'm going to do is I'm going to compute the projection of B onto A. Okay, so remember, there's a lot of A's in this formula. There's hardly any B's. So it's A dotted with B. That's the only place you're going to see a B. Times the magnitude of A squared times A. So that's this thing right here, which is what we're being asked to compute. So that's the projection of B onto A. At any rate, now that we've got that straightened out, this is pretty straightforward. In particular, the magnitude of A is 5. Okay, so let's just go ahead and do this. So dot product, so let's see, this is going to equal -3 times -4, which is 12, plus 1 times -3, so that's -3, over 5 squared times this vector. All right, that's going to be equal to 9/25 times -4, -3. And we could even write this like this, I guess, -36/25 and -27/25. So there's that. Might be a better way to write that, but I'm just going to put it in right here. Next, we're going to find the length of vector BD. All right. Well, this is going to be painful, I can see right off the bat. But here's this vector that I'm interested in. This is sometimes called the orthogonal projection. Notice that it's perpendicular to the this vector, and technically I know that BD is the opposite direction, but this vector B is made up of two components. You have the component that's pointing in the same direction as vector A, and the component that is perpendicular to vector A. Anyway, this is a right angle here, and so I'm basically going to use the Pythagorean theorem. So this projection will be one side of that triangle. Let me draw it down here. Let's see, can I redraw this in approximately the same orientation? Good enough. Okay, so this projection is this thing. So I'm going to have to do, okay. Let's see, the square root of 36 squared plus 27 squared all over 25. That's going to be this length, whatever that is. And then this one is going to be a little kinder, because that one is just 3, 1. -3, 1 is this vector B right here. And so that'll just be the square root of 9 plus 1, which is 10. Okay, so using the Pythagorean theorem, we'll call this x just for fun here. X squared, plus this nasty thing, 36 squared, 27 squared over 25 squared. If you square that, the square root goes away, and then the 25. That should equal 10. Oh, boy. Well, so this will be 10 times 25 squared minus 36 squared minus 27 squared. So square root of that. So 10 times 25 squared, what's that, 625, 36 squared, and 27 squared, all over 25. I'm just going to leave it like that. So that's that length there. I guess when I made this up, I didn't realize it was quite this nasty. Okay. Next. This is just an aside. I think you probably understand this, but just to make sure. Oh, yeah, there is this unit tangent vector business. So position as a vector function, we'll be interested in motion through space. And so as something moves, its position might be described by a particular function. The velocity, of course, is the derivative of position. So if this is r of t, then the velocity points in the direction of motion. Acceleration, by the way, would point in the direction of the change of velocity. Always going to be towards the inside, of any turn that you're going through. But anyway, getting back to this, the main thing for today is this unit tangent vector. So one way to think of the unit tangent vector is that it will be convenient at times to think in terms of a vector that is pointing the direction that you're going, but is only 1 unit long. And so this is the unit tangent vector. It's pretty easy to compute. You just find the speed or the derivative here and then divide it by its magnitude. That's it. So let's actually practice this. So suppose we have this particular vector function, and we're supposed to find the unit tangent vector. Okay, well, let's compute the derivative. And that's going to be, let's see, 3 times the cosine of 3t times I. Let's see, minus 3 times the sine of 3t times j, and then 8tk. Now at this point, I could compute the magnitude of this, but it's a lot easier to just go right ahead and compute this. The deal is that you can plug in the number that you're interested in once you've done all your derivatives. So in this case, I'm interested in t equals pi. So let's go ahead and compute r prime of pi. You'll see why in just a minute that this is fine. So this will be 3 times the cosine of 3 pi. Let's see, the cosine of 3 pi is -1, so this will be -3. The sine of 3 pi is 0, so there will be 0j. I guess I could emphasize that. And then 8 pi times k. Okay, let me do the magnitude of this. So this will be the square root of 9. We'll leave the 0 out of it because we don't need it. And then 64 pi squared. Okay, so the unit tangent vector is the velocity, or r prime, divided by the magnitude of velocity. Magnitude of velocity, by the way, is also the speed of an object. How fast are you moving? Okay, so this will be -3i plus 8 pi k divided by the square root of 9 plus 64 pi squared. And I don't want to simplify that. Well, I can't. There's not going to be any simplification. All right, so we've done 2 of the things, 2 of the cleanup things that I wanted to do. 2 more to go. Tangent lines, these are super easy. You've done tangent lines before. Let me remind you about linearization. That's actually how this looks a lot like a linearization. Linearization of f of x at x equals a is this. Y is equal to f of a plus f prime of a times x minus a. So I wanted to point this out because this is super similar to what's going on down here. It's a very similar situation. We take the position and take the direction and put them together to make a line. Same thing goes here. You have a position and you have a direction. Anyway, that's what tangent lines, it's really pretty straightforward. So let's go ahead and do that here. So in order to do this, I'm going to need the derivative. We did this one already, didn't we? This is 3 times the cosine of 3t I minus 3 sine 3tj. Okay, the thing that we haven't dealt with here is this. This says at this point. And we need to know what t is. We were given a point, but we're not given the value of t. And so here, we're going to have to solve for t. This is the x-coordinate. This is the y-coordinate. And this is z-coordinate. And so the x-coordinate must equal negative radical 2 over 2. The y-coordinate must equal the same thing. That really doesn't help me because sine and cosine are periodic. They just go up and down. So I don't know what the value of t is. And it could be a whole bunch of different things. But this next one is going to help me out greatly. Pi squared over 4 should equal 4 times t squared. I feel like I've made a mistake somewhere. Well, we're going to find out. Maybe I have, maybe I haven't. No, I think I'm okay. Yeah, I'm fine. Okay, so divide both sides by 4. I'm always worried about typos. So this will be pi squared over 16 is t squared. And that gives me t equals pi over 4, or t is negative pi over 4. So I need to know which one of these I'm dealing with. So let's check them out. Which of these works? So it's going to be one of those two. So let's try t equals pi over 4. If you plug pi over 4 into these two things, I get sine of 3 pi over 4 and cosine of 3 pi over 4. Sine of 3 pi over 4 is positive radical 2 over 2. The cosine is negative. And so because of this, I'm sad. What about this one? Well, there, when I plug negative pi over 4 into those, I get sine of negative 3 pi over 4, which is negative radical 2 over 2, and cosine of negative 3 pi over 4, which is also negative radical 2 over 2. So that one works. So this will be t, is equal to, what did we say? Negative pi over 4. Okay, all that's left is to compute the slope, or rather the direction, r prime of, pi over 4. And that's going to be 3 times the cosine of negative 3 pi over 4, I minus 3 times the sine of negative 3 pi over 4, j, and then this will be minus 2 pi k. All right, almost done here. Let me just clean this up a bit. So the cosine of 3 pi over 4 we said was negative radical 2 over 2. So this will be negative 3 radical 2 over 2. And then this will be plus 3 radical 2 over 2 because of the double negative. All right, final answer now. We can get the tangent line. The tangent line will be, I don't know, S of t. I don't know, we need a different letter because we've already got R up there. But anyway, you just take that point. Oops, let's make this a vector. And then the direction. I suppose another way to write this would be to write it in terms of x. Minus 3 radical 2 over 2t, y and z. And there you got it. Okay, one more. The final one is the biggest pain. Okay, so, oh yeah. I wonder if I can get this to work. Ooh, just a minute. This is too cool not to show you. Let's see, can I do it from here? Vector function cleanup. I have a link to Desmos. See if it'll let me show you this. Ooh, yeah. Okay, so here's the deal. When you, oh, wow. Never done this on my iPad. Okay, so when you have a function, a vector function, that vector function is generally going to be parametrized in terms of t, time usually is what we think of. And so here, this little slider here is just to show you sort of what's going on in terms of time. So here's t equals 0, and then we move over a bit. Oops, there's t equals 6. Apparently I jumped way ahead. But t equals 1, and then up to t equals 2. But that the distance that you move is not, like here, you can see the units there on my graph. On this curve, you're moving quite a large distance. When I get to t equals 3, 3, I'm here around 50 or 60. And when I get to t equals 4, I'm at 100. So I've moved quite a distance. So it's going to be convenient at times to to think in terms of parametrizing a curve in terms of arc length. So in order to understand how to do this, we have to think in terms of what arc length is. So arc length is the integral of the magnitude. There it is. So yeah, this is a little bit hard to quite to get, but so think of it this way, that you've got this thing here. So that thing is the speed that you're moving. And so if you want to know how far you've gone, then I guess I should probably change variables here. I don't know. Yeah. That's no good. I can't use an S there. I'll just use... Okay, I'm not going to like it. I'm going to put an X in here. There. But anyway, just to make it technically correct. So how far you've gone is going to be related to how fast you're moving. So you take your speed and you integrate your speed. You know how it works. Back in Calculus 1, you would do this. To figure out how far you went, you would do the integral of speed. So that's what arc length is. Well, let's actually literally do this. Let's find the speed of this thing, and then we'll do the the integral of that to get the arc length. Then we'll deal with the ramifications after that. But let's do those two steps. So first of all, r prime. And this is a bit of a pain. It's really not fun, but I'm going to do it with you here. So I've got 12t, so I'm just taking this r and doing the derivative. And then we've got -5 sine of t. Oh no, product rule. Plus 5 times, oh, that's going to be convenient. Give me a sec here. 5 times the cosine. Product rule. Okay, so that's going to be minus 5t sine. Okay, I think I got everything there. Let's clean things up. Notice those two cancel. You're left with 5t cosine of t times j. Let's see, this one and this one will cancel, and you're left with -5t sine of t times k. All right, well, there you go. Next, we're going to do the magnitude. And that's going to give me the square root. That's hard to see. I'll keep it under the blue. The square root of square this thing, 144t squared plus 25t squared cosine squared t. And then square this, and because it's negative, when you square it, it becomes positive. 25t squared sine squared t. Ooh, I see something fun. I don't know if you feel the same. Oh, no dt. I love it when this happens. Give me a sec here. There, hopefully now it's really obvious to you as well. Cosine squared plus sine squared equals 1. Let me get rid of this thing. And so cosine squared plus sine squared equals 1. So this gives me 144t squared plus 25t squared. Well, that's 169t squared. And hold on a minute. 169 is a perfect square, isn't it? It's just 13. So this will be 13t. Technically, this is plus or minus 13t. But if we restrict ourselves to positives, which I'm kind of doing, at least on this Desmos that I showed you, we'll just hope for the best, I guess, for now. Anyway, now, here's the deal. We're going to call this S. S is equal to arc length. So S is 13t. What this tells me is that when t is 1, we have traveled 13 units. So that's how far you've gone. When t equals 2, oh, I'm sorry. Wait, this is the speed. This is the speed. I need to get the arc length. Hold on a minute. This is the speed. Arc length. Okay, so this is going to be the integral from 0 to t of 13x dx. It's painful for me to change letters on you like this, but I know you probably just want to do the antiderivative, which, yeah, you can just do. Antiderivative of 13t is going to be 13t squared over 2. Just do it. And whatever, 13x squared over 2 from x equals 0 to x equals t. And that does give me 13t squared over 2, exactly what you would have expected. So it's technically the arc length from 0 to t. Okay, so now, arc length. S. S is used for arc length. So S is 13t squared over 2. What that means is that if you travel for 1 second, you have traveled 13 halves units. If you travel for 2 seconds, you have now traveled 26 units. If you travel for 10 seconds, you have traveled 1,300 over 2, whatever that is. What's that? 650 units. So that's why when we go to Desmos here, wherever it was, there it is, and we see this slider moving across, there it is, sorry. When t is equal to 5, it shoots off, this object shoots off, it goes really far. So when t equals 6, you've gone over 200 units. You can see there that you've moved quite a distance on this graph. Now it's not letting me pinch to zoom. I don't know why. Anyway, let's go back to here. And so what I'd like to do is I'd like to reparameterize the original curve. I'm going to have to rewrite this. Or 6t squared I, give me a sec here. R of t is 6t squared I. This is a little bit of a pain. Give me a sec. 5 cosine. It's 5t sine times j. And then it was 5 sine, or no, 5t cosine minus 5 sine. I'll go check to make sure. I mean, I should know I made this one up, but yeah, there it is. Okay, so there's my original function, and so notice here is I want to reparameterize, which means change the parameter from t to s. So what I'm going to do here is I will solve for t. When I do that, I get this. T squared is equal to 2s over 13, which means t is the square root of 2s over 13. That's supposed to be an s. Okay, so what we'll do now is we'll plug this in to the expression here. And so you get r of s is going to be what you get when you plug this in for t. So 6 times 2s over 13 times I. I feel like I've made a minor error. Just give me a sec here. At speed, arc length 13. That looks good. All right. I think I made a mistake somewhere else then. Okay, so this will be 5 cosine of the square root of 2s over 13. 5 times the square root of 2s over 13 times the sine 2s over 13. They look so much like 5s. They're s's. I hate the letter s, especially when I have 5s in the mix. Okay, that's times j. 5 square root of 2s over 13 times the cosine. Oops. Yeah. 2s over 13. And then finally this. Okay, and that's times k. All right, so what does this do for us? Well, let's go back to Desmos, and hopefully this will make it all clear. Okay, so what I've got here is I've superimposed this curve, but I've got, so if I get rid of that point, can I just get rid of it? There it is. And I've got that, you can see here, my expression right here is exactly that expression, so apparently I did do it right, that we had earlier. And if I move this slider, that actually moves that when s is 50, there we go, 50, then the point has actually moved 50 units. So I know that it's not exactly on the 50 there because this curve kind of snakes its way around, but the actual arc length is 50 units. And then if I go to 100, then it's moved 100 units. Once again, it's not right on the 100, but because this thing is curving. But that's the so that's what this does. Whereas the here, let's see, just to contrast, let me go turn this one on. Come on. Okay, so this one is parameterized for t, and so when t equals, say, 4, you're way over there at 100. Whereas here for the s, when you're parameterizing with s, then that moves in a much more, like, you have to go all the way to 100 to get where t equals 4. And so there, the parameter is the arc length. This will help us later on. For now, it's just a technique that is useful to have. So let's see, is that it? Is that it? That may be it. All right, so that hopefully, that's the whole deal. Vector cleanup, yeah. I think, whoops. Oh yeah, there they are. Yeah, I just want to make sure. Yeah, you had all of this stuff. Okay, so, you know, we're going to get through this together. Let me know if you have questions on any of this. The reparameterization is really the hardest thing, I think. So practice some of that if you can. Thanks for watching. Make sure you smash that like button.